All right, so this is where we are now. We have done the process of exponentiating a Lie algebra in 3 different circumstances. And the process we did was very literal. We took the Lie algebra, theta I, xi, and we simply exponentiated it. Exponential theta I, xi, where xi were the generators of the Lie algebras. All 3 of these had the same Lie algebra, which was fun. But of course, when we exponentiate it, we get different matrices, and these are not the same groups, right? SO3, SU2, and SL1C all shared the identical Lie algebra. And it was only when we took that algebra and sort of forced it into the metric preserving requirements that SO3 has and the metric preserving requirement that SU2 has. These are complex sesquilinear metrics. These are real orthogonal metrics. And this one isn't even metric preserving. It's just volume preserving. So we did those exercises, and we ended up with these 3 different groups that all share the same Lie algebra. So with that in mind, we now want to sort of study, okay, we need to learn a little bit about this relationship between different Lie groups that share the same Lie algebra. That's sort of where we're headed. And Gilmer wants to do that in a very systematic way by studying these 3, which are obviously different groups. And by saying they're obviously different groups, these are not isomorphic, right? You can't create an isomorphism between SO3 and SU2. You can create an isomorphism between SU2 and SL1Q, however. These 2 are isomorphic. But this guy is not isomorphic to those 2. So we need to understand that. So we're headed in that direction. And to get there, we're going to go through the notion of manifolds, of understanding these groups as manifolds just a little bit better. And that's where we're going to begin. So I'm going to start with SO3. SO3, I'm going to put in this little blue box, which was always our representation of the actual group itself. So there's the group. Matrix operation is matrix multiplication. This thing is, it's got topological continuity for the group operation and the operation of taking a group element and giving its inverse. Now, before we got into a habit of laying down these black lines to simulate the coordinates, so we're going to reverse ourselves and we're going to go back to the more classical appearance and talk about mappings that go from a chart or a chart mapping into R3, because we know this is a three-dimensional Lie group. And here is our R3, theta 1, theta 2, and theta 3. Those 3 numbers parameterize this entire group. And now we can't get lost in the fact that I don't see theta 1, theta 2, and theta 3 in these numbers here, because we remember the following formulas. So these formulas sort of, our theta 1, theta 2, and 3 are buried in theta itself. Theta, or theta squared is simply the sum of the squares, but theta is the square root of that, converts all of our parameters into these little unit parameters. So these guys are these directional parameters, and then there's the magnitude of theta, which is the magnitude of the parameters, which is the sum of their squares, or the square root of the sum of the squares. And this magnitude shows up as the argument of all of these trigonometric functions, and the trigonometric functions have factors that are drawn from these little unitized or normalized parameters. So I guess we call these the normalized parameters, and this is the process here of normalizing the parameter. So it's still true that any point out here in R3 can be inverse mapped through, if this is, say, a chart map we call gamma inverse. Remember, this is a homeomorphic mapping, so gamma inverse certainly exists. That's the whole point of being a manifold. I'm not going to go through everything about a manifold, but I'm going to try to review the words. So you review the language, right? We have manifolds involve charts in the actual group, and these charts are regions in the group that get mapped, that have their own chart mappings into R3, and these are homeomorphisms, so they have inverse mappings as well. So I can take any spot in R3 and go back into the group and I can find a group member. And the way I do it, as I've worked through this whole mess, I calculate all of these numbers. We can, if we are interested, we can see that the identity, or that the origin of this R3 chart, R3 coordinate system, will in fact give us the unit matrix, because if I take theta 1 equals theta 2 equals theta 3 equals 0, well, all of the sine terms, well, clearly what it'll mean is theta itself will be 0, right? The sum of a bunch of zeros. So all of the sine terms go away because they're 0. All of the 1 minus cosine terms go away because they're 0, which means all of the off-diagonal terms go away completely, but the on-diagonal terms just have cosine theta, which is 1, 1, 1. So it just so happens that, good news, the origin of the origin of the coordinate system, which is what this is in fact corresponding to the identity element in the group. It doesn't have to be that way. I think in an earlier lecture I really stressed that we wanted it to be that way. It's certainly not a requirement, right? You don't absolutely have to be this way, but it is in this case. Right, so, but now what Gilmore wants us to do is he wants us to start thinking about members of this group, but in a little bit tighter way. I mean, this is a great thing to know, and it proves to us that given the parameters, we can find the group element, so that's good. But we don't want to draw this matrix every time we want to refer to a group element. So he wants to give us a way of a quick notation to capture everything about a given matrix that we need to know. And the way he does it is he says, okay, well, we're going to take an arbitrary spot in the coordinate field, and we're going to say, well, that spot out there it's got a certain direction from the origin. We're going to treat this just like a regular kind of 3D coordinate system where it has unit vectors in the I, j, and k direction, except it'll be the theta 1, theta 2, and theta 3 direction. So if we were to put the unit vectors in there, it might look like this. And if we wanted to call them orthogonal, we would say, okay, we're going to pretend that this is a Euclidean system where these three guys are orthogonal, and we use all the regular Euclidean metrics to calculate, the dot products between, say, these vectors. And every point in this space is going to be represented by, essentially, a little vector made up of these unit vectors. And so if I pick a point out there, say located at theta 1, theta 2, theta 3, under these assumptions, let me go back to black. Under these assumptions, I can take these three guys, and I can say, well, what direction is this point from the origin? Well, that direction is going to be theta 1 hat, times, say, the I unit vector, which, well, let me not do the I unit vector. Let me say the E1 unit vector, plus theta 2 hat times the E2 unit vector, plus theta 3 hat times the E3 unit vector, right? These three together would add up and will create a vector which we're going to call, for the purpose, just to stay consistent with Gilmore, we're going to call this the vector alpha. And that will be a unit vector in the direction of some point that has coordinates theta 1, theta 2, and theta 3. Now, to really zero in on where that point is, I not only need the unit vector, but I need the magnitude. But the magnitude is clearly just theta, right? So the actual location of this point in this space would be theta times the vector alpha. Notice this is a vector, vector, and vector here. These are unit vectors. They're supposed to be E1, E2, and E3. And these are just real numbers, right? These are just the parameter divided by this magnitude, right? So that's just a number. They're also called the direction cosines, right? So the actual little vector that represents going from the origin to some arbitrary point is theta alpha arrow. So what Gilmore would like us to do is say, you know what, let's refer to the group element literally this way. But what he wants is he's going to say we're going to make every group element is going to be boiled down to an ordered pair. The first ordered pair is the unit vector in the direction of its little coordinate triple. and the magnitude of the actual full vector. So if this is the unit vector in the direction alpha, sometimes the full vector would be written as alpha. So he just wants us to say, we're going to now establish that any point in the coordinate space will be identified as its unit vector of direction and the magnitude it takes to get to that point, which I wrote theta here. So now I guess it would look like magnitude of alpha times the direction of alpha, right? But it is important to understand that the intent is for this symbol here to actually refer to a guy in here, right? So in principle, what it is we're using the coordinates to get from, say, the origin to some arbitrary point, but then the implication is that we're taking the inverse mapping and landing at some spot in the group. And this guy here actually represents this spot in the group that corresponds to these coordinates. And the coordinates themselves are kind of masked in this vector notation. So this is sort of one of the reasons that this subject is kind of tricky, right? Is there's layers and layers of just, convenient notations that accumulate pretty quickly. But this has to be thought of as a matrix over here in the group. And the reason this is all easily bound together is because it's a manifold. We can always know that every matrix in the group will have coordinates. All right, so with that in mind, let's now study the matrices in the group by looking at their coordinates. All right, so now let's have a look at these elements, which we'll call alpha and theta, where theta is, we've got our formulas for both of these things. And I'll put the formulas here as a reminder, right? So this is clearly the magnitude of this little vector in our little space. So let's draw that little space out, but we'll simplify it a little bit by just doing, so let's just look at it in 2 dimensions here. So theta 1 and let's see, theta 3, and so theta 2 would be coming out of the board, but we'll ignore theta 2 for right now. And let's plot just some unit vector alpha. Right, so alpha, and we know that we start at the identity, and we've got some unit vector alpha, alpha vector. And then we're going to just sort of march along in that direction, where alpha, the vector, never changes. So these normalized parameters will never change. The parameters, however, do change, and the magnitude changes. So at different points along this line, of course, you're parameterized by a single number now, and that number is theta, which is the positive square root here. So we just march along this line. And the first obvious thing, so we're going to study this, and we're going to see what do we come up with when we just march along this line. And the first obvious thing we discover is that eventually we return to the unit vector. Because if we march along a distance 2 pi, right, then everything kind of goes away, right? The sine thetas go away, all the sine theta terms go away, because sine of 2 pi is going to be 0. The 1 minus cosine terms, those guys all go away too, right? So the off-diagonal elements are all completely gone, right? And the on-diagonal elements only have cosine of 2 pi, and those are all 1. So if I go out far enough, I come back to the identity. And how far is far enough? Well, it's 2 pi. So I know that alpha bar 2 pi is the identity. So the reason this is important is, first of all, I guess I should say that it doesn't matter what direction you start in, right? It doesn't matter what these theta hats are. The direction you march through this group is all defined by alpha, which are these theta hats. I guess I lost my little vector there. But the theta hats, it doesn't really matter. The analysis gets rid of them, right? Because the things that are left is just cosine without any directional dependence. So it doesn't matter what direction you march off in. When you get to 2 pi, you're going to be at a boundary of things that are always equal to the identity, right? So there's going to be this sort of circle that's going to go around here that's always going to be the identity. And the reason that's important is, well, if I keep going, right, I'll eventually repeat the same process out here at 4 pi, right? And every even integer number of pi's, this will happen. I will constantly return to the identity. And the reason that's important is that when that happens, when you can take one of these matrix groups and you will look in the parameter space and you realize, hey, no matter how far in a line I go away from the origin in the parameter space, I will always return to the identity in the group, which is another way of saying a 2 pi, 4 pi, in this case, 6 pi, 8 pi, right? All of those equal alpha 0, which is the identity element of the group. Then we say that the group is compact, right? And that has a topological meaning as well that we can talk about later. But the point is that this is a compact group, and that is why. Now, not all groups are compact. The ones we're studying so far are, right? All three of these guys are going to be compact. But some groups are non-compact, and some groups are non-compact overall, but have compact subgroups. And that's very important to understand those distinctions. Okay, but even before you get out to 2 pi, something interesting happens. What happens when you get to pi, right? When we get to, say, pi, right? So all the way out here is 2 pi, but this is pi. What happens then? Well, the cosine of pi, right, is going to be -1, so it changes sign. Cosine of pi is -1, it changes sign. This number 1 minus cosine pi, well, that is going to equal 2. It's nothing obvious happens, right? I mean, this ends up being 2 times theta 2, theta 3. So it definitely depends on the direction you go in, right? In other words, we shouldn't expect a circle around pi to all have the same value in the group, right? It's not like 2 pi where everything on this circle is the identity, which is an interesting problem because remember, we're dealing with a manifold. And a manifold's a homeomorphism from here to here, so it shouldn't be that one point here ends up mapping to 2 separate points, right? That's an interesting thing to notice. Obviously, this manifold requires more than one chart to make sure that every point has a single set of coordinates and you don't end up with these degeneracies, right? But we're kind of going to put one chart over the whole darn thing and we're going to accept the degeneracy, right? But that's not the same problem here with pi. None of these points are not all going to be the same because you don't eliminate these direction cosines when you just plug in pi. But what is important to understand is that if I plug in pi, that's a terrible pi. If I plug in pi, what if I plug in negative pi, right? What if I marched in this other direction like this? And I end up at this point here, which is alpha negative pi, right? It corresponds to alpha negative pi. Remember, the way we're kind of doing this is this notation refers to the actual matrix element, not this point in the parameter space, although it's obviously the same thing. So, but what if I do negative pi and what if I do pi? So what's interesting is not that we can identify what this guy is. But what is important is if I put negative pi up here, the cosines don't change, right? Because they are symmetric, right? Cosine of pi and cosine negative pi are the same thing. So none of the diagonal terms change at all. The off-diagonal terms, that's a little different, right? What happens here is I get sine of pi is 0. I always draw these little graphs here. Sine of pi is 0. Sine of negative pi is also 0. So the sine terms actually go away, right, for pi and negative pi. So the sine terms go away. The cosine terms don't go away, but they don't change either. So whatever matrix element, or not matrix element, I'm sorry, whatever matrix corresponds to this point, alpha pi, it's actually the identical matrix that corresponds to this point, alpha minus pi. That's the same matrix. Now notice, what's important is that just because it's the same matrix does not mean they're all the same, no matter what direction you leave the origin. This guy right here is not the same as that guy right there. This matrix is not the same as that matrix. But it is the same as the one that would be right over here, minus pi from the origin. So while when you go out 2 pi, every point on the circle is identified with the identity element of the group. When you get to pi, you don't identify the whole circle, but you have to identify that point with the point reflected about the origin in a distance of minus pi. So this point and this point are the same matrix. Those 2 points are called antipodal. And the implication is actually quite profound that this happens this way. Because now we imagined taking a path along this line. And I draw it here in black. And as we get to this point, as soon as we get to this point, we are also at this point. We are at a place that is 2 detached points. Now it seems weird, like, okay, you can't be at 2 places at once. But in set theory you can, because this matrix element, right? I keep saying matrix element. This element of the matrix group, this guy and this guy are the same group element. So if I'm standing here in the parameter space, I must also be simultaneously standing there. And that's fine because, I'm here along this line, as I go up this line, every time I'm standing at a point in that line, I'm only standing at one point in the parameter space. But this point in the parameter space is identified with its antipodal point, and when I step on that point, I'm suddenly also on this point at the same moment, and that's fine. I mean, this isn't physics, right? This is mathematics. This is a totally plausible thing. Those 2 points are identified. So now, if I kept going, right? If I kept going right through this point, I'd ultimately end up at the identity. That's exactly the equivalent of keeping going from this point this way, meaning I'm stepping here. I'd consider myself here. I consider myself moving down this line to the identity. And it's equivalent, right? This point here, for example, I'll draw a little point right here. That point is equivalent to this point right here. And this point right here is equivalent to this point right here. When I say it's equivalent, I got to be a little stronger. It's identified with. It's not like they're different, but they're the same in some way. They are actually the same point. We consider them identified. When we talk about identifying points, that's an important topological distinction because it has to do with quotient spaces and how quotient spaces are made. And it kind of goes back to a lot of stuff we talked about in the What is a Manifold lecture. So, in some way, it's totally fair to say in the first instance that as I was walking down this line, I was actually standing on an infinite number of points. Like, let's look at this one. I was standing there at the same instant I was standing there, which was at the same instant I was standing there, which was presumably at the same instance. And all of those points sort of move in lockstep together, right? And as I move from here to here, I'm simultaneously moving from here to there. But that isn't exactly how we're going to look at it. I just want to make sure you understand the notion of the equivalency. Every point on this line is equivalent to exactly the point that exists pi behind it. So I guess the way we have to write that is alpha theta equals, or alpha theta, well, we already know alpha theta equals alpha theta plus 2 pi. Oh, let me write this in a better place. Hold on. All right, so this is the way I want to write it down. Alpha pi, which means any direction alpha, but I go out a distance pi, which lands somewhere on this circle, is always going to equal alpha minus pi, which is you go in this direction, you go, I guess I should write it in here. You go in this direction, but in an opposite magnitude, right? That point and that point will always be identified on this circle. And another way of looking at it, of course, is this way, which is minus alpha pi, where I just reverse the arrow, but I go a positive number pi. And then that point will still be identified with that point. So the reason this is important is because I want to talk about paths wandering through the parameter space. And a good idea of a path would be, okay, I'm going to start in the direction alpha, and I'm going to come up to this line, but I'm not going to touch the line. I'm going to turn around the path, and now I'm just selecting, the path is just a bunch of coordinates of theta 1, theta 2, and theta 3. Maybe you could parameterize them. So it'd be, if we were to parameterize them, we would write, oh, we're going to draw a path that's going to have the coordinate theta 1 of t, theta 2 of t, and theta 3 of t. So I have one variable t, and that tells me where I am along this path. And then I can wander all through this space. And as long as I never touch the red line, I never have this problem of degeneracy, right? It is degeneracy. It's the coordinate system. This coordinate system is degenerate at pi. And the degeneracy is such that if I touch this curve, the moment I touch this curve, right, the moment I come around with this line and I go like this, the moment I touch that curve, I'm suddenly over here, right? It's like a video game, right, where you just go off one side of the screen, you come on the other side. I suddenly touch this curve, and then I can just continue my path. It's really not a problem, right? I can then touch the curve again, and then I would pop up over here, and I can wander through the space. I could go back to the identity, and then the path would be closed. This drawing that I just made for you is a closed path, right? It starts here, and it wanders here, and it re-picks up here, and then it wanders there, and then it picks up there, and this is antipodal. This is supposed to go right through the identity. I guess it's not a perfect, I guess, this curve should really intersect, say, there, right? Because this has to be antipodal, right? So that goes like that. And then once the path sort of goes there and it wanders here, it comes back to the identity. This is a closed path. Now, and it could do this any number of times, right? I didn't have to close to the identity, right? I could have had a path that just sort of wanders in here and stops, I suppose, right? Those turn out to be not so interesting, but it certainly could go back and touch this again and then reappear up here and then just keep wandering. It could cross itself. There's really no problem. And it can even do this. It can touch here and then turn around and come back and just touch at a point, right? In other words, it touches at this point. Yeah, it's over here, but I stopped at that point. So I stopped at this sort of dual point, and I immediately turned around and went back into this parameter space here. And then maybe I went back to the identity, and that would be a closed path. So the point is if we're going to draw closed paths in the parameter space for this group, this is how we have to deal with it. We have to deal with the fact that we have this degeneracy at pi, and all of our closed paths are going to have these antipodal matches. Now, it's just really important to understand that just because this red line is here doesn't mean all of the points on the red line correspond to the same point in the parameter space. It was true that there's at 2 pi, right, there is a circle that goes around this guy at 2 pi where that is true, right, where all of those points do in fact correspond to the identity. The question is, well, wait a minute, how do I get there? How do I get to that part of the parameter space? And, you can imagine that you might start here and go here, and you say, okay, no, I'm frozen, I'm stuck because I have to reappear over here now. But that's not really true, right? I mean, these are parameters. You can pick these numbers. So you can be here, and when you're at that spot, you have this problem of degeneracy, but then if you move this way instead, right, now these points are doubly degenerate with guys in this part of the space, right? Everything out here is reproduced by something in here. So, you can head to this identity, but your identified partner is always heading to this identity. So there's no point in being out here is what I'm saying. This is a compact group, right? Being compact, everything is accessible inside this finite, bounded, and closed region. It's closed because you're allowed to be at every point, right? So it's closed. Every point is a limit of some sequence of points inside here, which is one of the definitions of topological closure. But it's also true that every point in this group can be found in this region, right? So it's compact in that sense. So anyway, that's really important. So for SO3, this is how you wander around the parameter space. You've got to understand that these antipodal points are the same. And one thing I want to mention before we go on to SU2 is one of the ways to understand a given point in this space. Like, let's say I chose this point right here, right? That point has coordinates theta 1, theta 2, theta 3. Just remember, this always will represent theta I times the basis of the algebra, right? Exponentiated, right? So it ends up as, the element of the algebra is taken by exponentiation to an element of the group, which we write down this way, right? So this is really identification. That's what this 3 triple equal sign is supposed to be. And so you can think of this as wandering through the algebra. I've been thinking of it as wandering through the parameter space, but it turns out that's totally equivalent if you think of this axis as, well, this is a way of understanding the algebra too. When I give you these 3 numbers, I'm giving you an element of the algebra. So this is wandering through the algebra, and that's usually what the way the books will describe it. They'll say, if you go through the identity or the 0 of the algebra, a straight line through the identity of the algebra, which is understood to be the 0 matrix, then that lifts into the group through exponentiation. So some path here in the algebra ends up being lifted into a path in the group, right? If this is the group, this path here in the group might correspond to this path here in the algebra. And this process of going from here to here is exponentiation. And the way you know what you're exponentiating is you take the algebra element and exponentiate it in principle. But we've already done all the exponentiation in advance, right? That's how we got this matrix to begin with. The problem, of course, is this notion of a path in the group is very bizarre because it's a matrix, right? So every point on this path is a matrix. The matrices are, in fact, close together, but the way you define close together is through the fact that it's a manifold, and this path is using the standard topology of R3, right? That is how we now create this notion of being close together in the manifold. We're borrowing the standard topology of R3 in order to define all of these ideas like compactness and things like that. So that's why when we look at this, we say it's compact. All right, so let's look at SU2 now. So we're going to do the same thing. We're going to have a look at our coordinate space, and we are going to start off in some direction alpha. And then we're going to say, well, first of all, we know that this 0 here, the 0 of the coordinate space, or the 0 of the algebra, to use the other terminology, better correspond to the unit matrix. So does it? Well, cosine 0 of 1 is going to be 1. Sine will be 0, so this imaginary part goes away. Likewise here, so the diagonal gets 1 and 1. And then the off-diagonal elements all depend on the sign, which is 0. So yeah, so the green spot in the algebra corresponds to the unit matrix in the identity matrix in the group, right? Remember, so this is the group. I guess I should, I've been putting blue lines to represent the group. That's the group SU2. I guess to be technical, we'll go SU2 complex, even though it's pretty standard to not. We very rarely use the quaternions, and U doesn't even apply to the reals. And the quaternions are so very, very rarely used that just writing SU2 is usually good enough. The point is, so now we know that okay, we've checked that the identity is where it belongs. What about this property that if you march along, you will return to the identity, right? We're looking for this notion of compactness. And that's certainly going to be true, but this time it's not true for 2 pi, it's true for 4 pi. So I'll draw it a little farther out. Out here at 4 pi, alpha 4 pi, you get your identity circle. And this will be a circle. At 4 pi, everything on this circle will be identified. So that's kind of interesting. Well, it's not interesting or not interesting. It's just a factor, the fact that this 2 appeared in the denominator, right? That's where the problem starts. But we saw that this kind of degeneracy existed in the other case as well. In the other case, we noticed, however, that there was this issue between, on your way to 4 pi, right? On our way out there, we ended up with this thing that had this antipodal matching, and that was at pi. So let's see what happens halfway between 0 and 4 pi. That's at 2 pi, right? Well, at 2 pi, cosine of 2 pi over 2 is the cosine of pi, which is -1. So that becomes a -1. The cosine of 2 pi over 2 is sine of pi. All the signs are going to go away at 2 pi. They're going to be 0. So you're going to lose this, you're going to lose the diagonal elements, you're going to lose this, and this is going to become -1 and -1. And notice that none of the directional cosines survive, right? So let's be clear. At 2 pi, this goes away, that goes away, that goes away, and that goes away. There are no direction cosines left. That means no matter what direction you go in, you're going to end up at the matrix -1, -1 on the diagonal, 0, and 0. So in any direction, when you get to 2 pi, right, you are at the minus identity matrix. You're at the minus I matrix in the group, which means that anywhere along this circle around 2 pi, right, at 2 pi, every point on that circle is minus the identity. So this is no longer about antipodal points, because remember when we did this for this guy, when we got here, yeah, it was the same as this point, but it depended on the direction. So it's not the same as that point. So this, like I emphasize this over and over again, this circle doesn't represent the same point in the group. Opposite parts of the circle does. In this case, at 2 pi, the circle, in fact, does represent the same point in the group. Where green is the identity, the circle is actually minus the identity. So I redrew it here a little bit, right? So here's our minus identity circle. I guess I should write minus I. Of course, here's I. This is actually our plus identity circle. I guess I'll just say plus I, even though it's kind of redundant. And now what you also know is that there's other redundancies here besides just the fact that this whole circle is minus the identity. But this point here, as it marches closer to the identity, you can tell that all of these points, if you subtract, what do we have to subtract from them? We have to subtract, 4 pi, right? If you subtract 4 pi, you end up with something down here. So this point here, let me maybe red, I guess I should use blue. This point here is equivalent to some point right, I've drawn things where I shouldn't have drawn them. This point here is equivalent to a point right here, and as this point approaches the identity shell plus I at 4 pi, this point literally approaches that one right there. The point being is that every point outside this shell here is going to fall into a 2 pi shell down here. And as this guy marches this way here, it's equivalent to marching as this point here. When I keep saying this, I realize it may not be clear. I try to highlight things or redraw them, but the point that I'm indicating right here is it approaches the identity along this strip. That's exactly equivalent to this point approaching the identity along this path. And therefore, everything outside this 2 pi shell is not necessary. And we will know because you march to this edge of the shell and you reappear, say, well, that's a good point. If you took this full line, it's the equivalent of drawing a line that goes to the shell and then back towards the identity. We'll talk about paths in this area in a moment, but the point is that this is compact, right? This is compact just like the other set, right? This group, SU2, is compact because we can get to every group element in SU2 by staying inside this 2 pi boundary. Now, what's different about this is the way its paths work. So let's consider some arbitrary path, right? Let me erase this. And everything out here, you know what? I'm going to erase this too because we're never going outside this circle. Why bother? Everything, the entire group is represented inside this circle. So let's consider a path inside this circle where the circle is of size 2 pi. It's not pi, it's 2 pi. So I'll draw a path this time. I'll leave the origin. I'll go down this way. And just like before, I can wander anywhere through this parameter space. Now, remember, I've suppressed theta 3. It's coming out of the board. But this loop I'm drawing, this path I'm drawing, it could go out of the board without any problem. And let me change the path color to blue because the axes are blue. So here's the path, right? And there's a closed path. We're going to talk about closed paths a lot in our next lesson. But what happens when I touch the boundary? Now, in the other case, when I touch the boundary, as soon as I'm on that boundary, I exist at 2 points at the same time. As soon as I touch the boundary here, I exist at 2 points at the same time. I exist at this point, and I exist at this point at once. And once I touch the boundary, I have access to all the paths that are available to me leaving the point from the other side. I can enter this point any way I want, and I can leave it any way I want from the other side. Or I can enter this point any way I want, and I can leave this point any way I want. Doesn't matter. But here it's different. As soon as I enter this point, right, I exist everywhere at the same time. It's not that I exist at the antipodal point. I exist on this entire sphere. It's a sphere, remember, because of the suppressed theta 3. So that's really interesting. When you come up here, you can now leave and head back instantly from any other point on the sphere. So for example, say I land here in the sphere. Well, suddenly I exist everywhere. So if I want, I can continue my path back from here, right? Or I can continue my path back from here, right? Or I can continue my path back from here. All of those would be legitimate closed paths. In other words, this path, boom, and then like that is totally legit. This path coming out to here and then coming back in this way is totally legit. These dotted lines I'm drawing, I don't want you to think that they're paths that are actually leaving our region, because they're not. They're not leaving this 2 pi region. Maybe the better way to write it is, let's see, I get rid of these paths. Maybe the better way to show it is to say, okay, I follow a path to this point, and then I can immediately take any other point and then come back to the origin if I want. And I have free access to do that to any point on the sphere, which isn't really saying much because it's almost like just continuing the path, right? It's just like, oh, okay, well, I could do that with this red path. I go here, and then I just follow some path along the surface to any other point on the surface, and I go back. Not a big deal. It's actually a little simpler to understand than, even though you've got this weird thing about being everywhere in the sphere at once, it's almost simpler to understand, because if you can be anywhere in the sphere at once, I'm just basically saying once you hit the sphere, You just arbitrarily wander to some other point on the sphere and then leave the sphere back into the interior. Leave the surface of the sphere back into the interior of the sphere. I think that's actually easier to understand than having to realize, wait a minute, you got to reflect and come back to only this antipodal point. And then you can enter the interior sphere again, but you can only do it through the antipodal point. That would be like forcing, in this case, it'd be like forcing you, once you hit the sphere, you must travel all the way around, and that's the only point you can re-enter the sphere. In fact, that's exactly kind of what we're insisting, except in the other case, the path does not traverse the points on the sphere. And in this case, the path doesn't really traverse points on the sphere either. You exist everywhere on the sphere at once because the coordinate system is redundant that way.